Hi everyone. So I'm first of all, I'm very sorry that I had to cancel our tutorial. I hope that nobody got to campus yet before I had the chance to announce that tutorial was going to be canceled. And if you did, I am very sorry. I did eventually make it to Scarborough campus at 6:10 p.m. even though I left my home at 2:30 p.m. So it was crazy, especially considering that we were gonna start working with normal models in this week, which is a very important topic. So I prepared a sort of selection from the textbook, which I thought would be helpful for you to solve the most common type of questions and problems about the normal distribution, and for you to sort of review and solidify your knowledge of the normal distribution, okay? And it's contained within this material here, which I will be posting to the announcement section along with the link to the video, okay? So I really encourage you, if you are unsure about any of the material, to go over this carefully on your own. I'll just explain a little bit what this is and what the procedures that we're doing here in general are. So when working with normal percentiles and normal distribution, you're typically given a scenario and you are told to, or you assume the normal distribution, the normal model for that given scenario, okay? And once you have done that, whatever random variable you are interested in, you're gonna try to convert your specific normal distribution to the standard normal distribution. You find the z-score, and because we know everything there is to know about the standard normal distribution, you find your desired probability using that distribution, okay? So that's the general procedure that's followed, and this specific procedure is asked in so many different ways that it's good to sort of know about some of the ways as is explained in a very detailed manner in this textbook section, okay? So here I just want to explain a couple of things. So in this scenario, there is a cereal manufacturer who has a machine that fills the boxes. And the boxes are labeled 16 ounces. So the company wants to have that much cereal in each box. But since no packaging process is perfect, there will be minor variations. And if the machine is set at exactly 16 ounces and a normal model applies, or at least the distribution is roughly symmetric, then about half of the boxes will be underweight. And this will make consumers unhappy and expose the company to bad publicity and possible lawsuits. To prevent underweight boxes, the manufacturer has set the mean a little higher than 16 ounces. So imagine that the manufacturer has a normal distribution, right? And they want to avoid sort of underweight boxes. So if they say maybe their mean when they're setting up the machine, if they configure it so that it's exactly 16, then many of them are going to be underweight. So what they want to do is they want to set it up higher than 16, maybe at 17, right? And then 16 is here, so then not many of them are going to be underweight. So that's the idea. And based on their experience with the packaging machine, the company believes that the amount of cereal in the boxes fits a normal model with a standard deviation of 0.2 ounces. Let's use the model to answer a series of questions about these cereal boxes, okay? So I just wanted to remind you of a couple of things. So whenever you're given a problem like this, it's always a good idea to define what is the variable, the random variable, or the value that you are interested in, right? And here you are clearly interested in the amount of cereal in the box, or the weight of cereal in the box, right? And you want to denote it with a letter, a random variable, because then you can work with just this one in your probability. Some of you will sometimes like just maybe write like probability that weight, etc., right, without naming. This is okay, but it would be preferable if you do it with an actual random variable letter, a big letter. What some of you will do is maybe even worse, where you would maybe say probability x, and then you'll do some calculations and you never say what this x is. So for best practice, it's always essential to name your random variable and to state the problem clearly in your mind, okay? And here also is a formal notation to notate what just happened. So this is saying that you're denoting with x the weight of cereal in box, and you're saying that x is, the squiggly line is for distributed. You're saying that x is normally distributed, and you have two parameters here. The normal distribution has two parameters that you have to specify, that you have to know. One is the mean of that distribution, so 16.3. The other is the standard deviation of that distribution, that is 0.2. So this is how you would denote what this problem is stating, okay? And after you do this, and you can read over the sections very clearly, because it tells you everything you need to know and everything you need to do to successfully solve a problem like this. One important thing that I didn't mention is also the nearly normal condition here. So this problem clearly states and tells you that the normal model applies and that you can assume the normal model, right? But sometimes if you are not told that, you cannot go around assuming the normal distribution for data, because it can have other distributions. What you can do is maybe plot the data, do a histogram, and if the histogram looks symmetric, unimodal, then you can sort of justify it. But also, histograms can look different depending on how you draw it, right? So if you have maybe very small bins, right? Very small bins. Right? Maybe you wouldn't say this looks particularly normal, because there's a lot of smaller values here, and it's kind of right skewed and asymmetric, right? But maybe you draw it with just 3 bins or 5 bins, okay? No, 5 would be too. Okay, 5 bins. Then maybe you will get something like this, right? Which would maybe like look more normal. So what I'm saying is like, this is a terrible drawing, but sort of depending on the bin size, maybe sometimes the normal distribution, like the histogram might deceive you somewhat. So there are other plots that you can use, which the book goes over. But most of the time you can sort of maybe draw a histogram and then say, oh, I'm assuming the normal distribution because my data seems to be unimodal, it seems to be symmetric, or it's historically been modeled as normal, etc. So you can justify it, but in this one you're explicitly told that it's normal. And I'm just telling you this because in some cases maybe you will have to justify it or be mindful that you are taking this step, okay? So, and then the book goes over the mechanics of actually how to find probabilities using normal distribution. And what this does is that it's a good idea to make a picture of whatever distribution you're working with. So here they made a picture of a normal distribution with mean 16.3 and a standard deviation of 0.2. And they located the value we're interested in, which is 16, in this distribution. And why are we interested in this 16? It's because the serial boxes on the outside, they say it's 16. So we want to find the probability that the weight is under 16, right? Because we don't want it to be under 16. So what the procedure is that you need to find the z-score. And to find the z-score, this 16 is called our cutoff value, okay? So you want to convert your cutoff value into a z-score if using the table of standard normal areas. So the reason why you do this whole conversion thing, right, is because you want to use the standard normal distribution to make these calculations, because we know everything about the standard normal distribution. It is simple to work with. So this one here, the standard normal, has a mean of 0, standard deviation of 1, and looks like this. So to convert what we have to the standard normal, we subtract the mean of our distribution from our value of interest, and then we divide by the standard deviation, and we find this z-score. And we go to the standard normal, and the z-score, negative 1.5, is around here, and this area that we find that's below negative 0.5 will be equal to this area here. In other words, the area under the curve to the left of our value of interest in our original normal distribution is equivalent to the area under the curve to the left of whatever z-score we found in the standard normal distribution. And the good thing about that is we will be working with the standard normal table, and it's easy to look up values from a standard normal table, okay? So we found 0.0668, so it's 6.68%, okay? So after you have found this probability, you want to estimate, you want to conclude clearly what you found, and which is that you think that the 6.7% of the boxes will contain less than 16 ounces of cereal, okay? So 6.7% of the time, customers might be disappointed. Now here's the important part. For question 2 and 3, I believe, I want you to look at it and to try to solve it, and then look at the solution carefully on your own time. Especially if any of this is confusing to you, because now the procedure is inversed. So the company's lawyers are saying that 6.7% that we found is maybe too risky, too high. So they want no more than 4% to be underweight. So the company needs to set the machine to put a little more cereal in each box. What mean setting do they need? So what should they set the mean? Like we were saying before, what should they set the mean so that the probability of being underweight is 4% at most? And please try to solve it on your own by looking at, you will be using the same formula and you will be using the standard normal table to infer what this is gonna be, okay? Maybe I need to make one thing clear. So maybe 0.04, right? So 4% means we want this thing, this 0.068 to be 0.04. So we want the area under the curve of whatever mystery value here to be equal to 0.04. So now this is an exercise in working with a standard normal distribution. Now the standard normal distribution goes like this, right? So you have values here, you have values here, and you have maybe negative 1.5 here, and then you have 0 here. So this is where we found our value before, because it's negative 1.50. So this last value here you find from the x-axis, and this this value here you find from the columns. So now we want to examine all of these like different values. We want to find the coordinates, like the values here that are closest to 0.04. It doesn't have to be exactly 0.04, the one closest to it. And then we want to infer what this is. Once we have inferred what this is, we want to plug it back to the formula and calculate the mean score, which is what should be instead of the 16 here, right? So let me know how it goes. If you have any questions, always please ask. Otherwise, this one goes over things pretty carefully, okay? Now here, maybe I thought it was also interesting to include, there's a section called What Can Go Wrong? So, as we were kind of saying before, we don't want to use the normal model when the distribution is not unimodal or fairly symmetric. So if a distribution is blatantly non-symmetric, right, you want to be very careful about using the normal distribution, because it's going to be harder for you to maybe justify using it, right? So this is a histogram of compensation of CEOs. And here we see that there are a lot of values here. So this is a highly right-skewed data. So if you see something like this, maybe you don't want to use the normal distribution because maybe you want to justify it very carefully, or have just no other choice but to use the normal distribution or something, okay? So that's what the point illustrates. And for the second reminder is that don't use the mean and standard deviation when outliers are present. So what this is trying to say is that if the data set has many outliers, then the mean and standard deviation are going to be affected by it. So I think maybe don't use this, maybe too strong, but if you do use them, be very careful in your interpretation of them, because this you have to remember that this was influenced by your outliers. And what some people do is they would trim the outliers so that the mean and standard deviation measures are more valid, right? And the third reminder here says don't round your results in the middle of a calculation. So if at all possible, don't try to round many of your results too early, if possible, because the standard normal table, when you're looking at values, right, it's very detailed. So it's sensitive to maybe small differences in values. And if you make too many roundings, then you could end up at a different probability, right? Although it won't be like drastic as long as you're in the right direction, but it's still a good thing to be aware of, okay? If you're, as much as possible, be accurate in your earlier calculations, especially for the z-score, or if you're finding the mean, if you're finding the standard deviation, okay? Because let's say you round both the standard deviation and the mean. So this is rounded, and then this whole thing becomes rounded, and then your z-score is, it's possible that it would end up with a different value, right? So don't do that. The last reminder says, do what we say, not what we do. What? I actually don't know what this means. But I think these were very... Okay. So I have the review of terms. So if you're unsure about any of these terms, you can ask me, or you can try to look at the textbook more clearly, or look at these definitions more clearly, but I just thought these were all very important definitions, okay? So now in the other video, I'm going to try to go over some of the problems from chapter 5. But this again will be uploaded, so if you're unsure about anything, please try to do the problem yourself, try to challenge yourself to do the problem yourself, and read the solutions, okay? Bye.